Okay. Okay. Buenas todos. Buenas tardes. Okay, I'm Hongtao Wang from Polytechnic University of Valencia, and here is my PhD topic. It's about heuristic about for the yard crime scheduling problem. It's a kind of it belongs to a very general scheduling problem, and the last three teachers are my supervisor. Yes, I have 3 supervisors, and we are working in a SOA group of Polytechnic University of Valencia. And okay, now here is the content of today's presentation. I must apologize for the previous abstract. Today we are not talking about a grasp. We are talking a new method. But the topic, but the problem is the same. And at first, let's introduce what I'm doing. And first of all, we are doing a heuristic method for yard crime scheduling. As we can see here, we have two types of container terminal configurations. And that's what we do, schedule all containers. Each container is a request. We schedule containers, and as in this in a terminal yard, every small block is a container. I mean, it happens in on terminal port. For example, Valencia port, for example, Barcelona port. And we have 2 configurations. One is the Asian configuration, and this one is the European configuration. The right part is what we've studied today in this research. Especially, we have extra input-output points in the European terminal layout. That's to say, all containers must pass by the input-output points here. And why we focus on yard crime? Because this is most slow and buckle and very time-costing part. And where it happens in the yard block with in a European terminal, as we talk about. How do we improve the loading efficiency? Similar. We just input a very effective solutions of our schedule. It's just so simple. Okay, and some backgrounds of my research is that first, the marine transportation is a crucial, not critical, crucial part of the today's trade, and the containerized trade has increased for 40 times from 1980s. And loading in the yard crime is the bottleneck of the whole process. And investing, and some people say, why don't we just put more crimes? The answer is yes, it's possible, but it's too expensive because, as you can see, this is our yard crime, a rubber-tiered gantry or yard crane. This is another one. All of them are quite expensive equipment. And here is the container. We have two types of containers. It's 20 feet equivalent unit and 40 feet equivalent units. And now let's say the operations research in the yard terminal. First, we have here operation research. For us, it's a kind of combinatorial problem, and inside this scheduling problem. Actually, there are a lot of scheduling problem. Yard crime scheduling problem is not the most famous one. The most famous one should be some floor shop scheduling problem. When you search scheduling problems, you will find there are far more papers on flow shop scheduling. It happens on factories, on productions. What we focus on is more like a transportation problem. And here we focus on the seaside. For some research, they do something different. Some research, they do berth allocation or key client assignments. This another total different area. And some other researchers, they focus on yard client loading. For example, key client and yard client. What do we focus, as we introduced before, this is the yard client. Of course, we have a key client, and we will say how they cooperate together in the next slides. And also, there are some other researchers, they focus on some other process. For example, post stacking. That's to say, we do some auxiliary adjustment on positions of containers. Okay, here, as I talked before, here is a very brief picture of the yard terminal. Here we have a yard client, key client here, and here is the yard client. That's what we want to. That's what we focus on. And here we have some vehicles and also input outputs. As we introduced here, this is our input output. This is another one, and they located in both sides, sea side and land side. In the middle side is the yard, and we also have some other carriers, some other vehicles like straddle carrier like this. And basically, we have yard, we have two sides. So the containers can get out to this way, to that way. And of course, containers also need to put inside to the yard. So they can go from the vessels and transported by vehicles, and then input output finally goes inside to the yard. So totally, we have two sides. We have out operations. We have get in operations. So totally, we have four kind of containers. As what I say, we have four types of containers: storage containers and retrieval containers. Storage containers is used to be stored inside of the yard. The retrieval containers is already here, and they need to be retrieved out of the yard. They may go to the seaside or land side. Okay. Now let's focus on the yard crime problem. Basically, I list all the main characters of this problem. These are quite complex problem. We have more than 30 constraints in the mathematical model, but basically it follows on our TSP problem, traveling salesman problem. And we use our single yard client. A single yard client go to schedule one container, another. For to load each container, we need to choose our input output points for every container. So totally, the root is our TSP tower, but it's because we only consider our single yard client in this problem. So totally, we have one yard client, one block, and we have m input output points, and we have totally n containers. That's to say n requests. We have four types of containers, and each container has a release time or due time. It's unique time. It's constant. It's a constant integer, and that's to say, for every request, for every container, of course, our request, we go with a time parameter. This time parameter will guide how we load the container by yard client. And And next, we have we have a time-based, parameter-based. We have time parameter to guide the learning process. And more importantly, we have an inclusive occupation. As we as what I show you before, here we have we have input-output points. We have one yard cry. That's to say, for any time, one input-output points can only hold one container. At any time, the yard client can load only one container. That is the exclusive occupation. So for clients, for yard clients, we have our usage time period from start client SC to finish client FC. For each input-output points, we have a start occupation time SO to finish occupation time FO. And totally these four variables are most important variables of our mathematical model. And next, once we start a loading process, there is no break. And what we know about the request, we know the tap, as we told before, we have 4 taps. We know the temp parameter. Each container has a unique temp parameter. We know the location. The location of the container is a coordinate. It has x, y, z. And actually, for one request, we must know the origin. We must know the destination. So for each container, we have two locations. Both of them are known. And also we have the positions of initial clients and the positions of all input-output position or input-output points. And the decision we should make is we need to sequence all the container requests. What's more, we should also assign the input-output points to each container. That's to say, we need to do both things together. And here, let's say how a client move to request. The process is we separate one load in 6 steps. From hoisting spreader, move over from the yard, and lower spreader, pick up container, move over the yard blocks and set down the container. Just like get up, put down, and get up, put down. Because every time the one thing we must notice this: when we load the container, we must go over the yard block. That's to say, we must put the container first and then go put down. And this is a loading move of a yard client. Maybe you wonder, how do we deal with our exact container request with a given temp parameter? Now it is. We have 2 types of we have storage and retrieval containers. This one is for storage. It's for a storage container. We have at first the container come with a release time, and the next step is we must assign one input-output points, like this one in the picture. And step 3 is the yard client must go to this input-output point to pick the container. And finally, with a loaded move, the yard client go to the destination location here. It happens for our storage container. But what about the retrieval container? This container is already in the yard block. We need to move the container out to the seaside or land side. At first, we also start our input load, and to arrive at the location where the container is located, and then we load the container to the input/output points here, and then the container will be delivered by the truck. And in this case, we also have a time parameter. That is we have a due for in the land side, we have a due date. That to say, this container must be finished before this time. For the retrieval container to the land side, we have a vehicle arriving time. Before the arriving time of the vehicle, we count this container cannot be put on the input/output points. This is how we cooperate input/output points and yellow crayons in our loading of a single container. Okay, here is the objective function of our mathematical model. We have delay, we have congestion and earliness. This part is a weighted delay. That to say, our containers must be the crayon finish time should be early than the release time, and this part is the delay. It means that how long you are late, and this part is the congestion, and this part is earliness. And to show this better, let me explain this in the example. Here is a Gantt chart of the yellow crayon scheduling problem. Here we have 4 requests, and request 1 to request 4. And for the first one, the first one is our storage container. It needs to be sent from the C side to the yard block. So we have 3 input/output points, 2 in C side, S1, S2, 1 in land side, land 1, L1. So for the first one, it's same. At first, this container will be loaded to our input/output points at S01 and finish at F01, and then the crayon will load this container, start from S1, finish at F1. And here we have our release time. This is exactly the time of this time the container arrived. And of course, we have another one. This is also a storage container here. We first occupy our input/output points, and then occupy the yellow crayon. Differently, we also have retrieval containers, and what we can see, here is a due time of retrieval containers. That's to say, the container must be loaded at this time. If not, you will get earliness or you will get tardiness. Of course, we also have our retrieval container request 4. And one thing we can notice that because the input/output points is the final stage, so for retrieval containers, they stop at this time. I mean, the finish time is on FO for retrieval containers. The finish time of storage containers is FC at this time, here and here. Okay, this is what we explained before. This is the congestion, this is the lateness, and here we have earliness. And for someone, I also list our comparison with our very famous flow shop scheduling problems. I added these sliders because the flow shop scheduling problem is more famous than our problem, and some of the comparisons are listed here. And first, the difference one is that our jobs is about the objective function, and because for this kind of for Flowshop scheduling problems, they usually use some different objective functions. For example, the make span, that is the total time cost, and of course, but for our problem, we use our lateness or tardiness based objective function, and and I think the most biggest difference is here is that we have our input, we have a dynamic input-output assignment. As we already know, every container must occupy one input-output container. But one thing is that the container they go with a given time. We can't promise at this time when the container come, we can't promise there will be a container waiting for you. So we must in this time you must give a very good assignment to input-output for I/O points. If not, you have to wait. It will result in big lateness. That's what I say. Our assignment of input-output is dynamic, and also the difference can be we have release time, and as we also have another difference that is it's possible to, that to say in this point I want to express our problem is more complex, more difficult than the compared Flowshop scheduling. Because it's hard, because for both problems they have two decisions actually. For our problem, we schedule containers, we assigned input-output, we assigned I/O for them. For Flowshop scheduling, they also have two decisions. They schedule and they assign factories. But for their problem, for the compared problem, their problem are easier because it's easy to know which factory can be better allocated. Okay, here this is a comparison of the problem. Now what we do? How we solve this problem? Previously we used the grasp method. The grasp method is simple, and we build a candidate list and we select with a rule, and we from selecting 8 items to build a solution, and then we use a local search, and then we build again with local search, and in these iterations we finish our we finish a grasp. And in this presentation, we do a totally different algorithm. It's iterative greedy. This I'm not sure how many of you heard iterative greedy before. Please raise your hands. Okay. You must be. How many people know more genetic algorithm, GA? No. Okay. It's these two methods are usually be compared. This is a very general heuristic method, just like genetic algorithm. And genetic algorithm is the most famous meta-heuristic method. And this one is iterative greedy. This method is proposed in the 2008 by Ruben, my supervisor. So naturally, I use this. And and it's a very easy method. And we have 4 operators: destruction, reconstruction, local search, and acceptance criteria. So at the first time, we should generate our initial solution. And here, actually, we use our grasp method to generate our initial solution. We just generate one, not a lot. And we start with our grasp solution, and we do a local search. And from from these two steps, we can get a good initial solution. And with this good initial solution, we start to iterate. We start two iterations. And first, we destruct this solution, and then reconstruct, and then local search, and then inner acceptance criteria. It's a very, very simple algorithm. We only have, this is the postcode, and it's a very simple. Do you have a pencil? No. And okay, and now let's start with our initial constructed solution. As we already know, we must build our sequence. This is a sequence, just like so, just simple. And for each container, we must assign one IO. We do two decisions separately. In this postcode, we do our assignment based on our SETR, based on a rule. This is a simulated ending time rule, and that's to say, once we have a rule, we fixed our sequence, and then we do another step. We assign this, and this is the general idea of the assignment is más o menos rule based, and this is a procedure, and this is the initial part. But for in this slider, this is the core part of iterative grading. So I want to give you an example to illustrate this process. As we already know, we have a 1, 2, 3, 4, and this is a sequence here. And what we do for destruction is that we destroy this solution. For example, we must give our parameter d. That is how many jobs you want to destruct. For example, d is equal to 2. That to say, we randomly choose 2 jobs and we delete it from the solution. For example, we choose 1, 2, and we delete. So the sequence now is 3, 4. Okay, let's use 5. That's the remind part. And now we must reconstruct. That to say, we want to recover it as a full solution. The process is very simple. We already have 1 or 2. We randomly select 1. For example, we select 2, and now we try. We try here. We try here. We try here. And finally, each time we test our objective function, and finally we will know. Okay, here is best. So we have a 3, 2, 4, 5, and in the simple and the next step we add 1. We add 1, and we test here. 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 So totally and we also calculate the object function. So finally, we will get a full solution. For example, we say, okay, here is the best. So we have this is a new solution, and finally this is a new solution. So here is a destruction and reconstruction process, and now we will. But I have to say, after this destruction, we don't promise this consider must be. We don't promise this solution be better than before. So we need to do it in a local search, and so we do a local search. This is another solution, and then we go back. We destruct, and we destruct and reconstruct like this, and then go to local search, and then destruct and construct. Oh, one process I must say, that is the local search. How many people know local search before or already use local search? Okay, much more than before. Local search, as you know, local search is a very common improving strategy to improve the quality of your solution. Here we use our swap local search. That to say, for every container we select one, we swap. A swap solution is we replace two containers. We replace the positions of two containers. We swap, and finally we find the best solution. We find the greedy one. And in this local search, we add one parameter that's better. That to say, when we search previously, for a local search, previously, if we test for a container, for example, for this solution, for a local search, we start for this local search, for example, we start 1 here. We test all these positions. Usually, we only insert it to a best one, the best position. For example, here. But in our local search, we say no. I want more. So in this local search, I select 2 or 3. 2 or 3 is the value of the better. So we choose more, and inside the 3 solutions, we randomly choose one. It's just similar with grasp thinking. And in this way, we insert 1, and for the next time we insert 2. For the third time we insert 3. So when all the containers are swapped, this local search will be finished. And if in the middle stage, if the solution is improved, we will do another one. We will do another search. So here is a local search, and one thing we overlooked, that is, we have a acceptance criteria. You may already know, after a local search, we get a new solution, pi double prime, and this solution must be selected. That to say, this is the new solution, pi double prime, and this here is the very initial position. Here is the solution of the last iteration. So we compare. The new solution will be compared twice with the last and the best solution. This is the last solution of previous iterations. This is pi best, is the best solution so far. So use this acceptance criteria. We can do something. For example, here we update pi. What is pi? Pi is the one to be destructed. And so we will say, if this new solution is improved, we will update this pi for destruction. Destruction is the here is the main course of the iterated greedy. And so we adopt a very strict condition here to adopt the pi. And if the new solution is better than best, we update the best. The interesting thing is here we use our simulated annealing method to adopt the pi. That to say, with a very tiny proportion, a weak solution can be also go to destruction. That's why even this, with a very, very little probabilities, if a solution is not improved, we can still accept to update as apply here. This is, so let me finish this whole procedure. Okay. Here is the main procedure. And finally, this is main operators of this work. Some future works are more fancy iterative grading methods. And if you have more questions, we can talk more about this. And now, thanks for your watching. And some papers cited in this work are listed. So thank you very much. Okay.
During the local search, you say you choose, you basically, if I understood correctly, you compute the value of the objective function for each container type.
Yes.
For instance, on the board, you wrote the first container, and you check the objective function between 2 and 3, between 3 and 4, and between 4 and 5. And then you select the top, the best outcomes, and you randomly select one?
Yes. Do you mean you want to ask some question about the local search, right?
Yeah.
Okay, that is, usually we only select the best one here inside among all positions, and we do a little change. That is, we choose more positions, but finally we randomly select one.
But it's not the best.
No,
One of the best, but not the best.
Yeah, not the best. It's a random one among top best.
I have a question because it was not clear for me. In the jar, you are putting you're putting the container in a place, but you have a tower of containers. You have several.
Yeah. We have yes. Let's say this picture. We have here is a tire. Here is a three. Yeah.
Imagine I want to take the one on the bottom. I have to take first one, second one, and then this, and three.
Yeah, actually, this problem is not. Yeah, it's another problem because we have a assumption that is all our request containers are located on the top stack. Maybe not on the top level, but on the top. Yeah.
I thought that you were also adding the.
Yeah, yeah, what you talk about is a post-stacking problem or pre-marshalling problem.
Yeah, pre-marshalling, I know that from Celia.
Yeah, Celia is doing the first thing. Her work is about it's about another thing. She's work is changing the positions in a very static occasion. But for my problem, it's more dynamic because we must load everything. We must give order. And okay.
You have shown here a procedure separated in 4 levels. One of them was destroy, then you construct. No?
Oh.
You have shown a routine or a
okay.
algorithm.
Yeah.
I think it's the first one.
I mean the iterative grading. Okay.
This algorithm is based in the ALNS procedure. Do you know? ALNS, Adaptive Large Neighborhood Procedure.
Grasp. Greedy randomly. Sorry.
No, it's because
variable search.
Variable VND.
ALNS.
A,
A kind of modification of BNS.
adaptive. Start with L. Adaptive. Large. Neighborhood search. Yes, it's similar. I know some works about not about the yard crime scheduling, but about floor shop scheduling. Adaptive large neighborhood search. As you can see, it's more about the local search. And I mean, as I told you, yes, it's similar. Both of them will iterate local search, but in different way. For example, we also use local search, but local search is not the main procedure of the iterative greedy. We want, that's to say, I mean, if I understand correctly, for adaptive larger neighborhood search, we may repeat our local search once and once again. But here we have a very different operator, that is destruction and construction, and we deliberately destroy this answer, because the answer after local search will reach a local optimum. We want to destroy the solution totally.
Yeah, but in this algorithm, you have a set of destroy operators and a set of constructing operators.
Yep.
Here you have only one destroy operator and only one constructing operator.
Sorry, what's your question?
In this algorithm,
Uh-huh.
you have a set of destroy operators
Yeah.
and a set of constructing operators. But here, in your algorithm, you only have one way for the solution.
Yeah, it's the method of the destruction is fixed. Every time we do we do something similar with different inputs, and that's why we call it iterative greedy, because as what do you say, when we insert, when we destruct and reconstruct, we always use our very greedy way. We don't know at this time, we don't know inserting this operation, it must be best. I mean, in the total, for the final solution, we don't know this step must work, but we still do. That's because it's a greedy procedure. That is the main procedure of the iterative greedy. We destroy deeply and we reconstruct a local search and do something else. And another difference is that it's about the acceptance criterion. It's totally different with that of ALNS. I mean, the acceptance criteria is also different with the adaptive large neighborhood search. That's the main difference in my mind.
No, but in this algorithm, you can use the same criteria rather than the same
Okay. And I think that IANS is that you are performing the local search inside of the greedy thing that you're doing. You're performing the local search while constructing and destructing the this is not. If you build, you destroy, you build, and then you perform a local search with the solution. It's some kind of thing.
Actually, I mean, in my understanding, they are for almost all the meta heuristics. They do something similar. They destroy and they local search. They destroy and they improve. They repeat this process. Just like it's also like the genetic algorithm. For genetic algorithm, you use some operators crossover or mutation. All of this is to destroy. But finally, you go on local search and they usually repeat. The difference, the most distinguished difference is how you destroy and how you accept this, how you accept. That's the main difference about iterative grading with other methods.
Okay, it's interesting.
Thank you.
I also have a question on the reconstruction part.
Local search, okay.
No, the reconstruction.
Reconstruction.
Yeah. So you destroy and then you rebuild. But
right.
When you reconstruct, you don't know if it will be better.
What I know is.
Can it be worse than the initial solution?
Oh, no, you want to talk about destruction, right?
No, reconstruction.
Reconstruction. Okay. Okay. Here we have a reconstruction happens after a destruction. For example, as I told you before, we have a 3, 4, 5. This is the remain part. We insert, for example, we insert one here, and here, or here. And now we test a solution. We first test this one, and then we test this one.
I get it. It's more. Can you be sure that the reconstructed solution is better than the always?
I can make sure because so far it's not, all of them are not feasible. It's not feasible because we still have, we still lack 2 here. But when we compare these solutions, we can find the best one. Maybe it's this one. We can say insert here, we insert in this position is best because that's what we can make sure. We don't know how it works for our final solution, but in current step, we know this is best. This position is best. We don't make sure in our final solution, one must be here next to between 3 and 4. But in current step, we know this position work best. It's for sure.
But in your example, you remove 1 and 2. But
yeah.
If you put 2 first, maybe it will be in the place that was better for.
Yes, a good question. Because we just give an example. We first choose 1. Actually, 2 or 1 are randomly chosen in each step. So next step, if we choose 2, the position can be totally different. Maybe 2 maybe it's better to put here or another place. So only when we test 1, we can make sure it's here. When we test 2, the solution is another.
You can do it sequentially, I think, because what you're doing is testing the objective function. Meanwhile, you are checking. So imagine you first put it once. You evaluate in each of the places between them, and you say, okay, this is the best one. And then you go to introduce the number 2, and you decide the place.
Yes, that's what I do.
I think it's not relevant the order.
Okay, you want to say first you test 1, but you don't insert really, and then you test 2, and you don't insert. You don't really insert. You test all the positions. This local search, not a destruction.
Okay. Just before we finish, we usually ask our speakers in the seminar about their experience in academia. For example, in your case, you've been there for 12 months.
I come from Polytechnic Ube, and actually it should be the 4th year of my PhD life, maybe the last year, hopefully. And I stay here for 3 months, short visiting to Federico professor, and because he's doing something similar. And I may leave in the initial days of last month. So I feel very, very happy to be here, and I feel a very strong academic atmosphere here in this department, far stronger than what I experienced in UPV. We have very friendly atmosphere, very friendly friends. as you are. So I much appreciate for being here for 3 months.
Thank you very much for your nice words.